Why? Well, this time I'm going to turn the staircase the other way for a reason which will become apparent in a moment. So this time, for A1, that will be this height, I'm going to turn it this way. Consider this rectangle of width 1 and height A1. All right? Then I'm going to go down until I hit the second height, which is A2. Are you see? And then go down just enough so that I can turn to the right and hit A3. And so on. Are you with me? So this staircase goes like this. Okay? Now, what happened is that let me forget about the first piece for the time being. Right? In asking whether this area starting with 0, right, the area under the staircase is finite, then that will be, if it is finite, then the area starting at 1 will also be finite, because the difference is just a finite piece. Is that right? If this is infinite, then the whole thing will be infinite as well. So asking whether this thing is infinite is the same as asking just this piece, starting 1 as opposed to 0 is infinite. Are you with me? And so what? Well, this time I'm going to look at this shaded area. What is that shaded area? Integral what? So this curve is what? Y equal to 1 over x squared. So this shaded area is 1 to infinity 1 over x squared dx, correct? That one we studied back in chapter 7. This, once again, is antiderivative negative 1 over x, and go from 0 to some big L, and you take that L to infinity. Is that right? So this is just an informal way of writing it. What do you get? Oh, I'm sorry. This is 1. From 1 to infinity. So what do you get?
1.
1. Yeah? Okay, this is 1, not 0. This is 1. Okay, so you get 1. That means that this shading actually is finite. It doesn't blow up. It doesn't blow up. And then this staircase from the second stair onward, this piece, it's below that, stay below that. And therefore this staircase from here, this rectangle plus this rectangle and so on, add up to the area which is smaller than the shaded area. And if shaded area is finite, so is this. And then you add one extra piece. That will be A1, right? Then you still get finite sum. And so that's why this conversion. So that's a key idea. See that? So we capitalize on our knowledge of improper integral back in chapter 7. So, this shaded region, we knew how to calculate it before. And so we capitalize on that knowledge to conclude that that series diverges and that series converges. And in doing so, we have to use this staircase. And it depends upon whether you want to prove that the series diverges or you suspect that the series converges. Then you turn either this way or that one. Right? Okay, so we formalize this, we're summarizing this by introducing what is called the integral test. And I'm going to phrase the statement of integral test in a slightly more general language than that in page 716. Okay? So, I'm going to phrase it this way, slightly more general. So, this is called integral test. So, the integral test goes like this. Let's f be a positive continuous function. My apology. I should do this let f be a positive, comma, decreasing continuous function. And to make it even more general, then I'm going to say this. Let f be, insert a word here. That's where it becomes a little bit more general. Let f be a function, okay? Still those three adjectives, but I'm going to phrase it this way, slightly more general than in the book. Let f be a function that is, add this word, eventually, we used that word before for the spring break, eventually positive, decreasing continuous function. So it's a continuous function that is eventually positive and decreasing. I care about positive, decreasing. Continuity is taken for granted. All right. If series AN happens to be the specialization of this function to natural number input values, then the integral test says that limit and, oh sorry, not limit, I mean sum n goes from 1 to infinity, converges if and only if a to infinity f of x ds converges for some positive a. So what it means is this. Suppose I have a function like this. I don't care what happens here. Could be even negative. I really don't care. Okay, but from a certain point, when I say eventually, that means that from certain point onwards, you find that this continuous function starts to be positive and decreasing. That's all I care. What happened before? You know, even for the first 1 mile, it's very wild, I don't care. So long as from a certain point onwards, it becomes, you know, positive and decreasing. And then, well, how about my series here? My series here, I don't care what happens at first, okay? And perhaps it's exactly equal to these function values, you know? 1, 2, 3, 4, 5, and so etc. Okay? And then what is important is that from a certain point onward, it's, you know, it's agreed with this function. Then I have two separate things. One is a series, and whether that series, that infinite sum, converges or not, right? And I have another problem, which is that you have this integral, whether or not it actually converges. You know, the integral actually converges. And the claim here is that if that is convergent, then that is convergent. If that is divergent, then that is divergent. They converges together, they diverges together. And so, apply to this case over here. This is exactly that situation, where the function f is the function 1 over x. Is that right? And where the series actually agree with the function. Right? It's just the function specialized to natural number inputs. And then the claim over there is that if you're interested in whether or not this series converges, then I tell you that that's equivalent to asking whether the improper integral converges. And you look at that, the conditions are satisfied. Our function over here is 1 over x. Isn't that eventually positive? Is that right? Decreasing, correct? And then continuity is taken for granted, right? Continuous function that is eventually positive and decreasing. So it fits everything there, and therefore the assertion is that if this converges, then that converges. And usually we say that if that is convergent, then this converges. If that is divergent, then this is divergent. Okay, so I just have to look at that one. If I manage to show that that is convergent, then this is convergent. If I manage to show that that's divergent, then this is divergent. It goes together. Got it? That's called integral test. And so you can see that in the assignment sheet, which is 11.3, I didn't assign that many problems. Do you notice that? And the reason is because most of the time, I mean, usually a logic. Most of the time, all these convergent tests are used this way. This integral test is most useful in establishing one single fact. That is, these so-called P series, right? This is P series. P means this power here. Okay? So the P series, convergent or not, that is the important. This is a very, very commonly seen series, and this series is very useful in determining whether other series are convergent or divergent by doing what is called comparison tests, which we're going to study in the next section. All right. So in more general case, oftentimes you're interested in comparing whatever series you are dealing with some sort of special series. Oftentimes P series. And so just for dealing P series alone, I can cite this this integral test. Then I immediately come up with the following statement. What statement? So this is called P series. So far we have learned that some important series. One is what? Geometric series, right? And we also seen some series which can be written in telescopic, sums, right? Okay, but so far we haven't really encountered that many kind of series. So the next important class of series that we need to be familiar with, and this is extremely important, is called the P series. P series means this. So 1 over x to the p's, oh sorry, not x, 1 over 1 to the p's power if you use sigma notation, it goes like this. N goes to 1 to infinity, 1 over n to the p's power. That is to say that 1, or maybe more, one over 1 to the p's power, that's still 1, plus 1 over 2 to the p's power, plus 1 over 3 to the p's power, plus dot dot dot. Okay? So this is called P series. And so the P series, and this is very important theorem. The P series converges if this P, make a guess. We previously looked at the first P series that we encountered. That is P equal to what? 1. 1, when p equal to 1 is what? Diverges? All right, the series diverges. And this is p equal to what? 2. So it looks like once b is greater than 2, then it begins to converge. Is that right? So converges if p is greater than 1, strictly greater than 1. Okay? And diverges if p is what? Less than equal to 1. Example. If somebody asks you,